we introduced RoboNinja, an adaptive cutting policy for multi-material objects. Prior works on robotic cutting mainly focused on single material objects, such as slicing a cucumber. In these cases, an open-loop policy is sufficient to complete the job. In this work, we aim to learn a cutting policy that works with multi-material objects, such as mangoes with soft exterior and a rigid core. To achieve such tasks, a robot needs to carefully cut off the soft exterior of the object while avoiding collisions with the rigid core inside. The cutting trajectory also has to both maximize the cut-off mass and minimize the energy consumption. Here is a demo of our robotic system cutting an avocado with a low-cost force sensor. The robot first lowers the knife to cut into the avocado when it then encounters a collision with the core inside. The robot then retracts its state to a few steps earlier. Meanwhile, the collision signal is used for an updated estimation of the core state. The robot then continues the cutting process based on the updated state estimation. After a few collisions, our system is able to iteratively update the estimation of the core and generates a physically plausible cutting trajectory to cut off most of the flesh of the avocado. To better resemble real-world scenarios, we execute the same policy multiple times with different initial rotation angles to cut off more soft flesh from different directions. Here is an example of cutting with a different rotation angle. Let's now delve deeper into how we learn the cutting policy. Before we start, it's worth noting that learning such cutting skills directly on a real-world robotic system is challenging and potentially dangerous. Therefore, we build an environment that supports multi-material coupling and physics-based energy computation to simulate the cutting process. More importantly, the simulator is implemented in a fully differentiable manner, allowing for gradient-based trajectory optimization. The cutting trajectory is first initialized with a pre-designed collision-free trajectory and optimized under the following three objectives: cut-off mass, collision occurrences, and energy consumption. The trajectories optimized within our differentiable simulator are then used for training the downstream cutting policy. We introduce our method, RoboNinja, which consists of an interactive state estimator and adaptive cutting policy. The state estimation network takes as input the collision signals and then estimates the location and geometry of the invisible core. The cutting policy takes as input the core estimation, the current knife pose, and additional tolerance value, and generates the cutting action at each step. The tolerance value controls the policy's conservativeness when encountering collisions, which is crucial for maintaining an adaptive safety distance from the estimated core. Furthermore, we design and build a low-cost force feedback system for deploying our method on the real-world UR5 platform. The force is measured by a strain gauge as an analog signal, which is then converted to a digital signal and transmitted to the robot controller through an AD converter and a Raspberry Pi Zero. To effectively cut through the fiber-rich material, such as mango skin, we add an additional horizontal, repetitively back-and-forth slicing primitive, in addition to our vertical cutting trajectory. Here is a video of the second cut with a different initial rotation angle. Note that this is the exactly same policy as what we used for cutting avocado. We can reuse the policy to cut many different kinds of soft objects from different directions, making it more general and practical for real-world use. We show more videos of cutting different kinds of fruits. Note that in practice, the knife may exhibit visible deformations, and the object pose may also be changed during cutting, which could disrupt the accuracy of state estimation due to misleading collision positions. However, our cutting policy is robust enough to complete the task even with inaccurate estimation of the core. We compare our method with a non-adaptive baseline on 3D printed cores and kinetic sand. The non-adaptive method tends to get stuck, although the state estimation shown in brown is close to the ground truth in gray. In contrast, our system is able to bypass the core after a few collisions and complete the task. We also compare our method with other alternatives in simulation. The cutting trajectory of RL is very jittering and becomes too conservative after a few collisions. The greedy policy is able to strictly follow the contour of the estimated core. However, it chooses abrupt rotations and therefore consumes higher energy. The nearest neighbor model and the non-adaptive version of our method both get stuck and fail to complete the task within 10 collisions. In contrast, our method, RoboNinja, is able to iteratively update the estimation of the core after every collision and adaptively adjust the cutting trajectory with optimized energy consumption. We evaluate all these methods on cores with both training and novel geometry distributions. Our method outperforms other baselines by a large margin in terms of success rate. Here are more real-world evaluations on 3D printed cores and kinetic sand. With a handful of collisions, our system is able to accurately estimate the core geometry and cut off the majority of the sand with a smooth cutting trajectory. We also evaluate the performance of our policy on novel geometries. We demonstrate that our policy trained in simulation has strong generalization capabilities and effectively completes the task with out-of-distribution cores. Thanks for watching.